Hello everyone. Welcome to the today the online course entitled Solar Photovoltaic Seed Evaluation. My name is Kyo Chan. I'm going to present during the next few minutes. Where I think green energy is going now in this day. Maybe you all have a burning question about how can I design my own PV system. Well, I think this is what we are going to discuss today. Uh, Photovoltaic of a PV system, I think is combination of a component they able to out to earn the power of sun in our own home of a business. Where this include all the component requirement to convert energy from the sun and able to it to our requirement. Typically, it is consisted two main components: a PV module of a server and the inverter. Depends on the topology for system. You may also require maybe a battery. Let's take a look at the typically grid connected PV system in action in the following 3D illustration. On a normal day, you can see with some up. The PV module on the top of this blue are bit converting of the incoming ingredients into the photo-generated power. The green connected solar inverter used in this system are also constantly to converting. This output for a solar module into usable H power. The PV system is able to meet the load demand of this household. And on the different day, if a very sunny day, the PV system is providing much higher power than what the loading required. Under such condition, the AC power is fed to the grid. In most countries, I think the customer can be offset his electric bill in this method. And this facility is called net metering. We can insert the same system topology in the following diagram. And here you can see the normal grid connected PV system. The grid connected PV system topology is especially very common in the country that have the supporting the solar policy. When the extra power generated by the consumer can be fed back to the electricity grid. In the grid connected system, I think they have the two main components: a rated PV module and another is grid connected inverter. In this case, PV module are responsible for the power generation. I think the PV generation power is not only able to meet the load requirement. And the following will introduce the cell to the module and the weight. I think the typical crystallized silicon PV module are made from the number of crystallized silicon solar cell. This cell are then connected to the PV module, which turn is connected together, and the other module to form a PV array. I think there are different ways in which the cell in a module can be arranged, which influence the characteristic for a module. And finally, let's take a look at the series connect of a cell. And finally, we can see the series connection. Here, the overcurrent voltage for each cell is at the out, whereas the current to the series of cell is constant, assuming a state condition. And finally, the second option is the parallel connection of the cell. Now, the voltage across all the cells in the parallel is constant. However, the current produced by each cell now is the opt. We can see the diagram. And finally, we are going to take a look on a module level. Here we can see the module in which all the cells are connected in series. With the data of a cell, we can now easily calculate the voltage of the entire module. This equates to the voltage for each cell. Let's assume voltage is 0.6, multiplied by the number for our cell, 36. This gives our total of circuit voltage of 21.6. Then the overall module show circuit current now is 5 ampere. And now let's change the arrangement in the module a bit. Let's now the two rows for 18 cells in parallel. The voltage across the two rows shall be equal. But now, how do we calculate that? We are now only have to multiply the voltage for one cell, which is still 0.5 volt, with the number for cells that are connected in the series, which is 18. This gives me our 10.8 volt for our circuit voltage. As we have two rows in parallel, we have to multiply the short circuit current by 2 to get the module short circuit current. If we do this, we get a 10 ampere for the module short circuit current. The product of the open circuit voltage and short circuit current are roughly equal to 108 volt in both module. However, the characteristics for the module are different. This has to take into account with the certain other components of the system, like the inverter and the battery, or other. And finally, we'll take a look how the PV module behave in the system. PV system, PV module, they respond differently depending on the weather and the condition and their placement. PV module performs best when related with the degree sunlight. Let's take a look at what the mean by the module tail and the orientation, and how can we maximize the PV module performance. The tail is a degree of freedom that defines the elevation of the pitch of a solar module with respect to the horizontal. And orientation is a degree of freedom that defines the estimates of yield of the module. With respect to the position, which in this case is geographic south. And on that different places and the people have the different practice and define the estimates. The most common reference point are the geographic north or south. Let's change the horizontal and the tail. It's very important of the lots of direct sunlight. And like the mentioned before, the most direct sunlight, the module received, the most energy is converted. Other affect the quite important role of the shading, and the temperature effect on the module efficiency. And that can have the significant effect on the performance of a PV system. So far, I think we have discussed the best of a PV system at which a low PV module plate inlet. And next, let's consider irradiance. To calculate the average power density per day, we can use this map, which shows the average year solar irradiance across the whole country. This sample parameter to estimate the energy potential of the central place on Earth, like Taiwan. They have the equivalent some hour, 4.5 hours per day. Usually this data we find in the map and estimate the advantages of some module. And now we will look at the important concept of the system efficiency. We know that the solar to the electronic conversion efficiency of a PV module could be at much as 20%. We also seen how the efficiency of the rate of the system component is less than 100%. To find the overall system efficiency, we were able to system to see efficiency root at each stage. Let's assume the solar spectrum is 1000 watt per meter. The PV array is 20% efficiency. Therefore, the power density percent and output of a PV array is 200 watt per meter. And then to balance of the system could be placed at a considerable distance from the PV array to protect the inverter against the weather condition. In this case, this route may be important. Depends on the length of the cable and almost for a current to them, this route can be around 1 and 2%. So in this example, we will assume the cable have a transmission efficiency of 98%. Therefore, this power per area go to the inverter is 196 watt per meter. And then we'll look at the inverter with the demands in the power electronic. It's very common to have the inverter that reach this power to the AC conversion efficiency greater than 97%. However, usually the efficiency of an inverter is damping depending on the power in which it operates. For the sake of simplify, we should assume average efficiency over 95 for the inverter. Thus, the base power per area person in the system is 95 of the 196, which is 186.2 watt per meter. And assuming the loose exchange at this distribution panel and dissipation in the cable carrier as power, we get over our PV system output is 186.2 watt per meter. This means the income the irradiance at 1000 watt per meter processed by the PV system is going to give our 186.2 watt per meter. In other words, our world system efficiency is 18.62%. And then we'll talk about the photovoltaic economic of the payback period. I think the economic in the field of the PV voltaic can be described as several label, like the manufacturer, installation company, or even the technology label. To comparison with other energy sources, we can consider the economy in the great connection. In the next, we will start our discussion at the consumer level. At this level, we will discuss the concept of a payback period. In finance, the payback period is defined as amount of time required to recover the cost in an investment. So, how can we translate this consumer level? Our customer, however, is house owner or even a home owner. We install the rooftop PV system. The home owner put up the initial investment that cover the cost of a PV system, and the cost recover over a year as the PV system offset the electronic bill, and they call the payback period. And then let's see the example of a payback period. I think this can be understand use a simple example. Let's look at the instance. Assume the install a 1 kilowatt PV system, and the initial investment costs over $4,000. The average electronic consumption in such that they can receive a new electronic bill of $2,000 per year. After installation of a PV system, there will be $100 worth of electronic is generated by the PV system each year. And next, we can illustrate this situation in a graph. Here we can see a straight line representing the initial investment cost. Since the PV system have no maintenance cost, the overall cost of the system do not increase over the year. As the house owner uses more of the power produced by the PV system, it offsets the electricity bill accordingly. In our example, the almost save is $800 per year. In other words, the house owner earns a return of $800 per year on their investment. As the year progresses, the saving is accumulated. At some point in the time, the saving will exceed the cost of the investment. The period of time from the initial investment to this break-even point is called a payback period. In this case, the PV system has a payback period of 5 years. And we have note that the payback period is not a fixed value, but really depends on the number of factors. The location of a PV system is one of these factors. From above, we have covered some general guidelines of a grid connect PV system. And that brings me to end my presentation. Thank you for your attention. Bye-bye.